Good afternoon. So last week you were testing the solubility of various organic compounds by trying to dissolve them in different solvents, organic solvents, as well as acidic, basic, and neutral water. And you were using your knowledge of the structure of the compounds and the polarity. Remember, it's like we were looking in lecture at the three-dimensional structure of compounds and identifying polar bonds. And from that, we concluded if compounds have a net dipole moment and are therefore polar. And you did the same with your solvents to sort of predict what the solubility should be. And you were following that famous rule that we all know about, like dissolves like, right? So this is what you found out last week, and we're gonna build on the same principle this week. But before we go into this, I want to sort of summarize what we learned last week. You found what we say by like dissolves like, that basically polar compounds dissolve polar or interact with polar compounds and non-polar with non-polar. So, this is just my summary. What I was just saying, polar organic compounds can be dissolved in non-polar organic solvents. Polar organic compounds dissolve readily in polar organic solvents, but not enough. They're not polar enough to be dissolved in an aqueous environment. This is where only small polar organic compounds can be soluble in aqueous solvent. Charged species. And this is what's going to come in handy today. And then, of course, inorganic compounds, right? It's like small salts like sodium chloride are readily soluble in aqueous solvents. So we're going to build on this principle. And not only today, but other labs as well. You're going to use the same solubility principles for crystallization, which is upcoming. And then later in the quarter, we're going to do column chromatography, where you have basically a solid materials like in a column, and you load your mixture of compounds on top and then use the solubility of the solvent and the interaction to that solid phase to separate your compounds. And today, or this week, we're going to talk about extractions, and more specifically liquid-liquid extractions. So all of these workups, those techniques that we're learning, are useful for working up chemical reactions that you're going to be doing throughout the year, and that we're going to be doing throughout the year, and you're basically just learning the techniques right now. So for the liquid-liquid extractions, an extraction is really the separation of a mixture of compounds, and as the word implies, liquid-liquid, we're using different solvents to differentiately dissolve the compounds into one or the other, right? So how we're going to start out is by taking a mixture of compounds, and we're going to dissolve those in a solvent, and then we're going to try to pull one specific compound at a time selectively in another into another solvent. So this is where the extraction part comes in. So we're going to add another solvent to this and remove, hopefully, just one specific compound from that mixture. Okay. As I was saying, it's like for reaction workups, this is really important to purify your compounds or to maybe extract something out that you don't want in your reaction mixture. So since we're working on trying to separate different compounds and we're using different solvents, if the solvents would mix with each other, that wouldn't be helpful, right? And what do we call it when two liquids mix with each other? Anybody know?
Miscible.
Miscible, exactly. So this is not what we're going for. What we want are two solvents that are not, don't dissolve in each other, and we would call that immiscible. Okay, so it's basically just two M's in front. So this is what we're shooting for. And there's many examples out there. It's like a lot of things that you guys are very familiar with is salad dressing, right? What do we have in there? We've got water or vinegar, and what else?
Oil.
Exactly. So the oil is usually has long hydrocarbon chains, so it's very nonpolar. the water is highly polar, as we know, so they don't mix very well. And there's many examples out there. We'll get back to this point in a second. There's many examples out there that won't mix with water. Here's just some common organic solvents that we use for this kind of liquid-liquid extraction. Diethyl ether, not soluble with water or immiscible with water. Same with ethyl acetate. Dichloromethane is another common one, and hexane. One of the things you need to think about is when you have in your flask, if you have two liquids and they are immiscible, you're going to form two layers. For our experiment, it's going to be important to keep track of which layer is the aqueous layer and which one is the organic layer. So that's where knowing the densities comes in really handy. Water's density is about 1 grams per milliliter. Most organic solvents are less dense than water, so they're going to be on top. They're going to be the top layer. The only exception are chlorinated solvents, such as chloroform and dichloromethane. They're more dense than water, and they're going to be the bottom layer. So it's very important that you keep track of that. Especially later on, you're going to be switching solvents, and you might extract with ether first, and then you extract later with dichloromethane, and your layers are going to switch. So make sure you use those densities to always keep track of what's the upper and the lower layer. And this. So in the previous slide, the statement that I had on there, right here, is that most organic compounds are soluble preferentially in organic solvents. And that is true. However, there's a few functional groups, organic functional groups, that we can manipulate so they become more soluble in an aqueous environment. And I don't know if you guys remember, it's like from our a little bit of chemistry that we've learned so far for organic compounds. What do you think those compounds could be?
Aldehydes?
Not aldehydes.
Acids? Carboxylic acids?
Carboxylic acids and amines, exactly. So you guys are going to be looking at a mixture of carboxylic acid, a neutral compound, and an amine compound, and we're going to manipulate those to separate all three of those. So we'll talk about the first two of the components that are in your mixture first. One of them is going to be orthotoluic acid. So here's our benzene ring, carboxylic acid, and it also has a methyl group right here. Okay, and the neutral compound that is mixed in with this is 9-fluorine. And this compound looks like this, has a ketone in it. And then on each side of that 5-membered ring, we've got a benzene ring attached to it. Is that how you spell it? Yeah, just to make sure. 9-fluorine, okay? So both of these compounds have a fair amount of nonpolar components. Like we got this nice aromatic ring right here, which is nonpolar with the methyl group, but we do have this carboxylic acid, which is slightly polar. And then this 9-fluorinone has mostly a nonpolar component, a little bit of a dipole moment in the ketone. Both of these are going to be soluble in ether. Okay? And that is what you're going to dissolve those your mixture in, is in ether. So now we need to manipulate one of them to make them more soluble in an aqueous environment. And one of the things we can do, since this is an acid, we can just do a straightforward acid-base extraction or acid-base reaction. So we're going to take some sodium hydroxide and we're going to deprotonate that acidic proton and basically form a salt. So now we have a charged organic species, organic compound. Okay, and this is going to be soluble in an aqueous environment. So we just decrease the solubility of this compound in an organic solvent, but we increase the solubility in the aqueous environment. So, and decrease solubility in the organic solvent. Okay, and this is the key part of why this experiment works. So instead of just adding some base to ether, which wouldn't be very soluble, we're actually going to use like a 1 molar solution of sodium hydroxide, and we're going to mix it with the ether that these compounds are dissolved with. And from mixing the solvents, we're going to be able to transfer enough NaOH and get the telluric acid in contact with the sodium hydroxide and deprotonate that proton and make this salt, this carboxylate salt. So why don't we look at how the setup looks at this point. So you will be using what we call a separatory funnel, which looks like this. It has a stopcock on the bottom, and we can put a stopper on top. And this is a great funnel from the shape where you can easily see 2 layers. So what I have prepared is actually sodium hydroxide solution. I put a little bit of dye in there so it's easier to see. And I brought some ether, so we'll just pretend that you dissolved your compound in the ether. And I should have brought a funnel and safety glasses, so don't do it without those. So we're just pretending that we have our mixture of chemicals in this ether. And before you pour, you always need to make sure that the stopcock is closed. If you happen to forget, you're going to place a beaker underneath to catch anything that will spill. So that's the easy thing to remember. So that's your safety card. So now I'm pouring my sodium hydroxide in there. And do you guys remember what we said from the densities? Is that going to be on top or going to be on the bottom?
It should be on the bottom because the ether is less dense than the water.
Exactly. Thank you. So that should go straight to the bottom. And it seems like it is. So I'm showing you a few things to take into consideration when you're doing this. I did have some videos up on the PowerPoint presentation, which is loaded up on Canvas. Get to it. So make sure you watch those. The first video gives you some nice basics on the technique and how you do it properly and everything. And then the second video talks a little bit about some of the pitfalls, some of the confusion that can arise from doing extractions. And we just don't have enough time to go over all of those. So once you have your 2 layers in there, and I would not call them upper or lower layer. I would call them, this is our ether layer, this is the organic layer, the bottom is our aqueous layer. So always make sure you keep track of those and where your compound is. So to do the extraction, we will need to mix those. So the first thing you're going to do is place the stopper on there, invert, and then you're going to vent. So this is important. You probably didn't hear the hiss, but a lot of the organic solvents are volatile, so they build up pressure if you shake them too much. So you want to release pressure. Make sure you also have your finger on the stopper so it doesn't slide out. And then you just want to gently rock back and forth a few times, and maybe, especially at the beginning, vent to release the pressure. You're going to rock back and forth a few times. And then you vent. You might have heard that hiss. That was a little bit longer. Especially ether is so volatile, you really do want to vent quite a bit. So after you've rocked back and forth about 20 times, you're going to put your subfunnel back in, remove the stopper. And it's always good to have a paper towel so you don't get your work area dirty or transfer contaminants from the table into your flask. So now you're ready to separate your layers. What should have happened is that you have your organic compounds in here. The base should have now interacted with the telluric acid and made the carboxylate out of that and be transferred into this bottom layer here, the aqueous layer. So you want to separate those 2 layers. So you're going to drain the bottom layer into a flask that hopefully you labeled aqueous layer, and you're just going to open the stopcock and let this drain. And when you get close to the interface, you want to slow down and just drain it carefully. Since we're trying to get compound out from the ether layer, it's okay to leave a tiny bit of aqueous in there because we're going to repeat this process a few times. So it's okay if not every single drop gets transferred. And you do want to make sure that you don't get any ether into the bottom layer. If that happens, you could always pour it back in and try your separation again. If you have to recover the top layer, if that is the one you're interested in, then you would make sure that everything from the bottom layer gets transferred out, and then you would pour the top layer into your flask, and that's a cleaner transfer. One of the things you need to watch out for when you, and we can just do another quick one. So this would be our second extraction here, adding some more sodium hydroxide. And again, you want to just put the stopper on and vent, and sometimes these are tricky. One thing you want to avoid is shaking really heavily, because that could lead to emulsion. Now you just saw how much pressure I built up too. So that's something you want to avoid, because, and the second video shows it very nicely. It's like how you can get an emulsion. And this is really just a colloidal mixture of the two solvents that won't break up very easily. And there's various tricks that they talk about that you can use. So at some point you're going to encounter that and need to be able to separate those two. A lot of times just rocking gently and waiting if you do get an emulsion is all you need. So that is the basic concept on how this works. One of the questions I do have for you is, do you think it's good to just do one extraction with a lot of sodium hydroxide, or do you think it might be better to do several smaller extractions?
I would think it would be better to do several smaller extractions because you have more chance for the molecules to interface that way.
And that is exactly right. Although you might think, like, hey, I'll just use a lot of solvent and then I can get that all transferred. That is actually not true. Typically, you want to do about 2 to 3 extractions with smaller amounts of solvent. So there's your book on page 116 and 117 has a nice calculation. You can actually go through the math. And it's all based on the solubility of the compound in your organic layer versus the solubility of your compound in the aqueous layer. And this is, you get a constant basically. It's like, it's called the partition coefficient. But I want to show the results of that calculation. If we start, let's say we have 1 gram of our organic acid dissolved in 50 milliliters of ether. And we're just going to try to do 3 extractions with 15 milliliters each of the sodium hydroxide. So after the first extraction, let's say we can extract 60% of our compound. So what we get is 0.6 grams of the organic acid in our aqueous layer, and we get 0.4 grams of the organic acid still remaining in the ether layer, right? So when we do our second extraction, which I just did here, we should get another 60% from what's left over transferred into the sodium hydroxide, right? So that gives us another 0.24 grams in the next batch of sodium hydroxide, and then 0.16 grams remain. If we do it a third time, we get more of the sodium, more of the organic acid into the sodium hydroxide layer, and very little actually remains at this point in the organic layer. Okay, we can combine all these 3 layers, and we were able to extract pretty much 94% of what we had originally in the solution. So that is a pretty good recovery. If we did only 1 single extraction at a higher volume, we don't extract quite a bit. And we only get 82% of that organic acid transferred into the aqueous phase. So that is not as good. You will actually do an exercise on this for your pre-lab. I'm going through this calculation using a different example. And you will see that the amount of volume you use does make a difference. Because here we're using 45 milliliters of NaOH. You know, in each one of these transfers, we only transfer 60%. But overall, it's like we use the same amount of sodium hydroxide because we use a total of 45 milliliters here as well. Okay. How would doing on time? Sorry, I have to ask the questions. Like
20
how we're doing on
minutes.
time. How much? 10 minutes?
20 minutes.
Oh, 20 minutes. Okay, so we'll end the lecture right here. Thank you.